When designing micro-optical components like this, one of the biggest challenges is the thermal expansion. If you want to find out more, stick around and we'll check it out. To understand those design challenges, we first have to take a closer look at the coefficient of thermal expansion, the so-called CTE. In this picture, in black, shown is a material. At normal temperature it has the length L0, and if we now heat it up, it's getting longer. This means at higher temperature there's a difference of delta L. And if we take a closer look at this in a mathematical way, here we have an equation. On the left-hand side we have delta L divided by L0. This means this is more or less the change or the relative change of the length. On the right-hand side we have delta T, the change in temperature, and there's a coefficient in between. This is the CTE, the coefficient of thermal expansion. This CTE is a property of the material, so it means every material has its own CTE. And if we take a look here at this graph, once again, the length difference and the temperature difference, we can see that different materials have different slopes. This means different CTEs. For example, polymer has 60 times 10 to the minus 6 per Kelvin, brass is at 18, and glass has 3. So basically this means if we are combining glass and polymer, we have a factor of 20 between the two materials. What does happen? Here in this case we have material A, which is for example brass, and we have the material B, which is for example polymer. And if we now heat it up, then we can see that both materials are expanding freely, but material B is expanding a little bit more than material A. That's no problem at all. But the question now is, what happens if we bond two of those materials together? And this is sketched down here on this screen. Here the two materials are bonded together directly. This means if we're talking about metal, this can be a welding seam or something like that. Now, if we heat this stack up, then the blue material is expanding stronger than the green material, and this means it causes the whole stack to bend. This is a situation we want to avoid in our components. There are two other situations in the middle where the two materials and they are bonded together with an adhesive, and the adhesive has quite a certain thickness. So this means the adhesive, which is relatively soft, can equal out the stress between the two materials, and this causes the material to expand more or less freely without bending too much, and the stress is compensated. It is obvious the softer the adhesive is and the thicker the adhesive gap is, the more stress can be compensated. A solution to this problem, which is more a mechanical solution, is depicted here on the right-hand side. Once again, we have the two materials, the two different materials, but we put a kind of a leaf spring right and left to this stack. And this causes the whole setup to expand, once again, more or less freely, even if one material has a higher CTE. It does not bend through because the leaf springs are bent in kind of an S shape. And this compensates the stress between the two materials. This is necessary, for example, for those components used in transceivers, because a typical delta T is between 0 degrees Celsius and 80 degrees Celsius. And we have to combine materials like polymer and glass and brass. I hope you learned something today. If so, please leave a comment and see you in one of the next videos. Bye-bye.